Okay, so today nested list, functions, randomness, and colors. So let me skip through the slides that show kind of the functional outcomes of the various stages that we're going to visit today. So first we're going to do nested list. So we're gonna. Last time we did nested for loops, right? A loop within a for loops, and then we can create a 2D array of points. This time we're gonna store everything in a two-dimensional list or a 2D list as well. Then with that, like every point stored in a 2D list structure, as you will see in a moment, it's fairly easy to create pattern based on those grid points over here, which is a simple diagrid patterns. But you can use it to create a hexagonal and octagon or diamond grid patterns, as you will see in a moment. Then we're gonna do functions. Function doesn't have a visual outcome, but hang on. Okay, then we're gonna learn how to generate random numbers and use those random numbers to generate random looking geometry. For example, that bunch of points. Then we're gonna learn how to control the randomness. So most of us think that random is something that we cannot control, but as you can see in this pattern here, we can control the amount of randomness. So we get a gradual shift from completely order and deterministic slowly to randomness. And then the final topics is how to generate colors. Color is good for visualizations. How do I jump to an immediate slide without having to quit the front slide? All right, we generate colors, but here we not only can we do a single color, we can like have a little rule or map to vary the colors in a gradient manner. Yeah, okay, so those are, so today we still essentially deal with lines and points. Like we are not really going to touch curves and surface until next week. Next week we're gonna dedicate almost entire letters to learn about geometry in Rhino Common. Today is still fairly much about Python more than Rhino geometry. So we still work with the simple Rhino geometry just to get something on the screen, right? But next week we're gonna deal with curves, surfaces, like free-form curve surfaces, and wraps, okay? And well, there's not a big topic, which is mesh, but like mesh usually like a long topic is going to take half an hour, like half a lecture in itself, so we're going to do that probably in late November. Okay, so let's go to the first topic of today, nested list. So why it is important to know. So raise your hand if you know what is a data tree in Grasshopper. Actually, let's do the opposite. Raise your hand if you don't know what is a data tree. Okay, a few people. Okay, so in programming, there is no such thing as a data tree out of the box. There's just there's only a thing called nested list. Data tree is just a Grasshopper way to have a visual equivalence of nested list. Okay, so what is a nested loop? Like we did the other day, or nested loop is like a loop runs within every iteration of a bigger loop, right? A nested list is basically a list of elements where each element is a list itself. Okay, so a list of lists. Okay, so each element itself is a list, and each of these like smaller lists, I call it child list or smaller list, can have different length. Okay, but in this example, we're gonna create like a bunch of like child lists with the same length because we're gonna create a 2D grid of points, so they kind of equal in both dimensions. All right, so how do we do this? So again, before we go into any geometry, just look at a simple example with numbers only. Okay, so my nested list, so this is the variable that store our nested list or two-dimensional list. Okay, you will see a moment why I call it two-dimensional. Even though when we write out in this manner, it looks like a linear or like one-dimensional, but it's actually can be represented by a two-dimensional representation. So this is a list of 3 elements. So I have a pair of square brackets. So this is clearly a list. Inside a list, I have 3 elements separated by this comma and this comma. Okay, and each of the elements themselves are lists. Okay, and each of those element lists or like child lists has different length. Okay, or we can also do it this way. We can create an empty list first, and then we append the first list to this mother list, right? So append, but like what we append to it is not a single item, but like a list. Okay, but this list is treated as a single item. So from the mother list point of view, it's just a single item, even though when we look into the content of item, it turned out to be like a list. Okay, but from an outer point of view, it's just one single item. Okay, all right. So I hope you understand why we have square bracket enclosed inside round bracket. Round bracket is just, because this is a command, we need round bracket, but the input to round bracket is a list, which is contained inside a square bracket, a pair of square brackets. Okay. Okay, so that is how we create a nested list manually, by manually listing every element. So now, how do we retrieve an element in a list? Well, you know how to retrieve a single item in a normal list, right? So if we say my nested list and we give it index 1, it will give us the first element. This is the 0th element, and this is the first element. So the first element is this sublist here, 2, 3, 4, right? And then if we do the index operator again on the sublist, then we get the actual number. Okay. So my nested list, the first index will give me the first item, which is this sublist, and then I do the index operator or the square bracket operator again, and this one will give me, guess what, number 2. Okay, agree? All right. So this nested list is useful because inherently it represents a two-dimensional structure, like a table, okay, or a grid of points. This one I wrote it in like a linear manner, but we can perfectly visualize it or represent it in this way, right? So, well, a good example of a 2D grid of numbers rather than points. We're going to do 2D grid of 3 points in a second, but this is like a 2D grid of numbers. In mathematics, it's called matrix. So we can store a matrix perfectly fine using a nested list. Okay, so this is what a mathematics notation looks like. But inside programming languages, we can start in a nested list like this. So it's a list of rows of number. Okay, so this is the first row. This is, okay, we should say the 0th row because we count from 0, and this is the first row. And matrix is just a list of rows. Okay, and for matrix, the row must have equal length or equal number of elements. Okay. And now if we want to retrieve a number at, let's say, row 0, column 1, then we just say the matrix name and then give it the index 0, 1, which is very intuitive because in mathematics we also address each of the element using the index, right? The basically just 2 numbers, 2 integers. The first integer is the row and then the column index. And if we write the matrix using a nested list in Python, then retrieving an element as index 0, 1 is like almost identical to what we normally do in mathematics. So it's feel natural. Okay, so that is a list of numbers. Let's do a list of points. So if you have a list of point 3D object, okay, and the point 3D are stored in variable A, B, C, D, E, and F, right? This is the graphic visualization, but in programming we have to like store it somehow, right? So rather than having 6 variable A, B, C, and D, and E, and F lies around unstructuredly inside our Python script, we can put them in a nested list like this, okay? And then if we want to retrieve the point at row 1, we count a row from the top actually, so row 0, row 1, so row 1, and column 2, so 0, 1, 2, which is point F, right? We just say points and then give it the row index and the column index, okay? Alright, so you're gonna see the moment why storing points in this way is gonna be useful. So now we just learned how to generate these this 2D list of points first, right? We not quite understand why is it useful yet. Okay, so right, so in the next example, we're gonna generate those points. So this is a manual way to do it, like we manually build out the structure, but of course we cannot go very far if we manually specify everything in like a big fat line. So we're gonna do a two-dimensional list using some simple algorithm. So last time we already used nested for loops to generate a 2D grid of points, right? So rather than manually specify the coordinates of each point, we use a for loop to have an algorithmic way to generate it. Now we're going to do similar, but last time we store everything in a big fat linear list. This time we start in a two-dimensional list, okay? All right, so points. So this is what we did last time. Yes, we have one single list. This list is just one-dimensional. It doesn't it's not a nested list, right? And even though we use a for loop to generate the points in a 2D grid manner, but when we add to the list, we just add it to the end of the list, and the list just grow linearly. Okay. So the structure inside the list doesn't really match the visual structure of the points, which is fine. But later on, when we want to do some logic that connect the points together to form, let's say, architectural curtain panels, or some diagram pattern, it's gonna be hard if everything is addressed using a traditional linear index. Okay. So actually we still have not come to the point where we're gonna create a 2D list yet. But let's say that we already have all of those points stored in a 2D list. This slide will explain why is it useful to store things in a 2D list. Okay, we can create this pattern, for example. So how do we generate this pattern? So basically, this patterns is we visit each of the points, right? Which, let's say that this is the point that has index I and j, which is at row I and column j. Okay, so we are at the point as I and j, and then in order to find the neighbors. Okay, so that is the index I and j of this point. What is the neighbor? The neighbor is this one in the same row, right? So the index is also I, but the j is here I use reverse. So I is actually represent the column and j is the row. So I is the column. So this one has the same j, but I is add 1, right? So I plus 1j. Okay, and if you want to retrieve these neighbors, knowing I and j, right? So you're looking at a certain point ij. You want to retrieve this neighbor. Actually, we do this neighbor first. So I and j plus 1, and then I plus 1 and j plus 1, and then after we retrieve those points, drawing those two lines is easy. Okay, so by using a two-dimensional index, we have a very easy way to look up to the next column and the next row. Okay, so okay, so there's one slide missing, the slide where we create the two-dimensional list. Let's see if we can add it in. This slide must be from. Okay, so I will have to do it live, and then I will add a slide right in this second. All right. So let's start up Python. Okay, so the output's going to be, I get O points. I think I coded O geometry, not O point. Okay, so I coded O geometry. All right, there's no inputs for now. Okay, so import rhino.geometry, standard routine. Okay, so we're gonna have for loops to generate the point and add them in an empty list. Okay, so we have to create that empty list first, or that list is going to be a two-dimensional list, right? So, but we have to initialize to an empty thing first. So point plural equal to empty list. Okay, now we have for I in range 0, 50. Okay, so for each column I, we're gonna do the J for the entire column. So for J in range of, let's say 0, 50 as well. Oh, that's equal. Not. I forgot to press shift on my keyboard, so that's why. So. Okay, the x coordinate for our point is just I, right? So the spacing going to be 1 unit, so that's why I will also give us the x coordinate of the point, and y coordinates go to j. Okay, so we are creating a mini program that runs inside the j loop. Okay, all right, and the z coordinates, I'm gonna give it a fancy formula so that z varies according to I and j. Okay, now we can create a single point. Okay, now add rg.point3d x, y, and z. Okay, this is just a single point. Now we have to store this in this list. But if we append it to this list, then the list just like grow in like linearly in a one-dimensional manner. So we have to group all of these points to one row first. Okay. And that row corresponds to, one single completion of the J loop. Okay, so here's the trick. Let's watch me do first. Okay, so every time I run, so I gives me one row, right? So for every time I run a row, I have to create a list that stores only points of that row. Okay, and then at the end, I'm gonna append that row. And again, row is a list, right, itself. So I'm going to append the entire row to the list points, okay? So points consist of, so point is a list of row, okay? And each row is a list of points. That's why we make it two-dimensional. Okay, so here, let's watch first. I'm going to create an empty list of row, okay? So every time this loop starts from a new value of I have a brand new empty row, okay? And then I use the smaller loop inside to fill in the contents of row. So row append point. Okay. And after the for loop finished, then my row has been filled with like 50 points according to J, right? So at this one, if I type row will actually give me the list of 50 points. Okay. And now I'm gonna append rows to points. Okay, so now you can follow. So you add in this line and these two last line, all right? Okay, you notice that I only append row to points after the entire for J loop has finished. Okay, so look at the indentation here. Okay, if I do it inside the for j loop, I will get wildly different results that completely unexpected. Okay, now whether what it look like, you can figure it out in your head, but it's not that obvious to begin with. Okay, all right. So now we just need to output points. So O geometry, which is the output name, equal to point. Actually, if we output, we're not going to see anything at this point. Hang on a second. Yeah. Okay, if we run this, even if you don't get any error, you won't see anything on the screen. I will explain why. Oh, we're missing the math library, so we have to import math as well. Sorry, import math. So even if we run it, and if we don't get any error message, we don't see anything on the screen. We won't see anything on the screen. However, if we hover the mouse over the output, it actually sends out some output. But instead of sending out 2,500 points, the output is 50 Python list. Okay, so here's the thing. The output is a list of lists, right? So when you output a list of lists, and even though each sublist inside that list of lists has a points, has a bunch of points inside, the Python component is not smart enough to go into like 2 level deep of list. So when you give a list of something, it just output that bunch of something. It doesn't smart enough to know that something itself is a list in order to go further and retrieve all of those points. So that's why it stopped at the level of the first list and say, hey, I give you you send out a list of 50 items. Each item is a Python list, but I didn't bother go inside each of individual lists and get a points out. Okay, which is fine because our goal here is not to generate those points. We just like we're gonna keep this list here inside the script, and then we're gonna use the points in the next part of the script to generate the list of lines pattern, and then we output those lines. Okay, so the lines is what we want to output. The points is just for internal computing. It's not the final output. Okay. But if you happen to want to output it just to check if the logic is correct, you don't have to do this step. Okay. So this list store everything in a 2D manner. I can have another list but store everything in a flattened manner. Okay. All right. So this is it. And this list will basically behave just like what we did last week. Okay. So whenever we create a new point, again, you don't have to follow this step. I'm going to save the file. In addition to append the single point to row, so we're going to do an additional thing. We're going to append the points directly to the flattened list. Okay. So now so after this thing finished, we're gonna have 2 lists: points, which is a 2-dimensional list, and points flattened, which is just a normal list. So our data will be duplicated. Okay, so we have twice as many points as we needed, but they are stored in 2 different manners. And then if I send flattened points to the output, I can see the result. Flattened.
Line 16.
Append. Yeah. Okay.
Without the D.
Yeah. Thank you. Good. Oh, geometry. Now I have to. Here we go. Okay. Okay, so we have 2 lists. This list is only for visualization, but this list is what we are going to use to do the paneling logic, because everything inside this list is stored in a more structured manner. This one is like the structure is very difficult to work with because it's just like a big fat linear list. All right. Okay. Let me make this save. Okay, now in the next part, we are going to carry on. So now we have a list of points, right? Now we're gonna generate a bunch of lines, but this line we don't have to store it in a structured manner. We just store all the lines in a big fat linear list. Okay, so an empty list of lines. All right, now we're gonna use the for loop again to visit all of the pair of possible index I and j. Okay, now so previously I runs from 0 to 50, right? Range 0 to 50, but this time the for loops only run from 0 to 49. Okay, now the reason will become clear in a moment. All right, so for each of the index, if you look at the diagram before, okay, so okay, we use the for loop to visit each of the index I and j, and whenever we have an I and j, we can retrieve the point. So we just say point square bracket I square bracket j to get the first point, and then if we do point square bracket I plus 1 and j, we get that neighbors, and then similar, right? And they are just point 3D, okay? And then we're gonna put them into the line constructor command to get the actual random common line, and then we're gonna append that lines to the list of lines here. Okay, all right, so I do everything in quite condensed manner. So for I from 0 to 49, okay, so first I retrieve the points, right? So this is a point 3D, this is another point 3D, right, at the opposite corner, and from these 2 points I can put them into the rg.line command. Now this whole thing will give me one single line, right? And I start it in a temporary variable called line, and then I append that line. This line I appended to the list of lines. Okay, so that's one line, and I'm gonna do the one for the opposite diagonal directions. Okay, and then I just output lines. I think we can even shorten it, but this should be good enough. So all right, lines, which is empty, and then for I in range 0, 49, for j in range 0, 49, line equal to rg dot line point position I j points position I plus 1 j plus 1, right? Okay. All right, 2 minutes exercise. Can you modify those to, instead of having an X pattern, let's do a square pattern, okay? So square pattern, we need 4 lines. Yeah? Yeah.
Is that so that it's not confusing? Like, can't we just put output geometry equals square bracket?
Yeah, you can perfectly do that, except later on when we do this kind of logic where we hook up a timer to Python, it will, if you have a variable name that happen to be the same name as the output, it's gonna cause some weird things. I mean, there's a reason for it, but it's gonna be kind of annoying to work with. So that's why I only send out the output at the very last minute. Yeah, at the last line of the script.
Do you mind scrolling up a little bit? That last one. Just, there's kind of issues with redundancy.
Excuse me again.
There's issues with redundancy. Is there that way?
Yeah, sure. So of course, if we're interested in line, clearly redundant. But let's say that each line represent, like each group of 4 lines represent an entire surface. In that case, it's not really redundant. But here we don't do surface yet, so we just like pretend it's a square, and yeah, okay, they coincide. But yeah. If you want to reduce the redundancy, so here's how you do the logic. So for each, the pattern is now an L shape rather than a full shape, right?
Yeah.
But then you're gonna miss the last row and the last column.
Yeah.
But then you have to write 2 separate for loop to only run at the last row and the last column to cover for it. Yeah. Okay. All right. Just a side note. Here I separate these 2 lines into. Or here I've written this thing as 2 separate lines. But of course, if you later on when you used to like condense everything and like merge everything into one big fat lines, I can take this one. Okay. Rather than storing it in line, and can like cut it and paste it in here. Okay. So I don't need this temporary variable anymore. All right. Okay, but this is entirely optional. It just it doesn't make the code run any faster. It's not like much more efficient, but like sometimes it's cleaner if you can read through many nested commands like this. Okay. So of course, this way seems to be counterintuitive at first, because when we speak in every language, we have the points first. So the points make up the line, and then we append a line to list of lines. But when we read code in a nested manner, it's kind of opposite to what we say in English. So we append what? Append a line. A line what? A line made from 2 points. And upon what? Upon retrieve from the list. So it kind of takes some time to get used to. Okay, because this notation is opposite to what we actually think. We think from the most inner item to the most outer item, even though we write from like the outside first. Okay. So this is just to make a further comment. So the patterns that we create give you the impression that like that the geometry, whatever geometry that we create, like the lines, for example, has to attach to these points, but they don't have to directly attach to the points. For example, these 4 points are merely there in order to these 4 points are only there so that we can compute the midpoints. Okay, midpoint here, midpoint here, midpoint here, midpoint here. And let's say our panels go from the midpoint to the midpoint to the midpoints. Okay, so yeah, as long as you have a logic to get geometry from those 4 points, then it's like give you some rule. It doesn't the geometry doesn't have to like directly touch those points. Okay, so now compute the midpoint. You already know how to do that. So anyway, we're not going to do it here, but that's possibly going to be your assignment for this week. You can go a bit crazy, not crazy, but like go one neighbor extra. So here the logic only involve like a group of 4 points, right? So I and then the +1 point, but you can totally have a logic that involve not just the +1 neighbor, but the +2 neighbor as well, right? Okay, but if you have the +2 neighbor, then you have to be careful with the index here. So the logic of the point is like the range go from 0 to 50, but when we do the panel index, we only go from 0 to 49 because, you know, this logic only need to go to the next to last one, right? And then because we gonna add 1 to it, we're gonna reach the end. Okay, so I hopefully see why we have to like stop 1 before. If somehow our logic involve the +2 neighbor, then of course we have to stop like 2 steps before we reach the end of the list, right? Or the grids. Now, if I accidentally go to the end, which many people will make the mistake, even I still make the mistake these days because it's so natural that we visit each element, you will get a classic mistake, the classic error message, which basically index out of range. Okay, so if you are at the last element and then you add 1 to it, you will be out of range. Okay, and you get the classic error. So index out of range 50. Okay, so now this is not very helpful. Like, okay, line number 23. Okay, so it so you always need to step back and so in this case it's kind of clear, but like in many like real case, when you see this message, it might take a little while to figure out why you run out of index. Okay. Sometimes you run out of index because when you write this code, you generate the X, Y, Z, you generate a point, but you forget to add it to the list of row, or you forgot to append the row to the point. So this thing is like empty. And then when you try to retrieve something, you get an error message even when I is equal to 0 because point is empty, right? That's also a common mistake. Like we create a point, but we forgot to put it in the list at the last minute. So, okay, so. Okay, so all of this pattern can be generated from just a 2D grid of point and be creative with the index I and j. So This pattern seems to be counterintuitive. It would be counterintuitive if I say that this one is related to a square grid point or like just a regular grid point. But yeah, you can. But you need a special if statement to distinguish between the odd row and the even row. Okay, so each row has an index I, so you have to look at see if I is even or odd, and then you do the logic slightly different for the odd row and the even rows. Okay, so all right, that is nested list that is used together with nested for loops. Okay, so nested list and nested for loops. Nested list is whenever you want to process a nested list, you almost always process it using a nested for loops because they kind of naturally go together. All right, so let's go to the next topic, which is very important because it's called functions. So everything that in the Rhino common is basically just a function. So I have been kind of avoiding using the word functions because I haven't explained what it means up until now. So I've used the word commands, okay? But now, you know, the actual terminology is functions. So now you know exactly what a function is. So a function is, yeah, think of it as a command which perform an actions. But we already have a bunch of commands, right? So what do you mean by like learning about commands now? What is different from the code that we have been written so far? Because the code that we've been written so far, it did perform an actions already. So what is the difference now? Okay, so there's many cases where the codes need to be repeated multiple times. So when you write a short segment of code, a block of code, for example, if you have a list of numbers and then you want to write a short piece of code to compute the sum of that numbers. Now we did it last time, right? This algorithm to sum up everything in sum up everything from a list. Okay, let me remind that logic first. So we have an input list called my numbers. We're gonna want to sum it up. So we have to create a variable that store the sum. So the sum is gonna be 0 at first, and then we're gonna have a for loop to visit each element in the input list, and then we're gonna accumulate. Well, in this case, the sum accumulate means just add it to sum, right? So sum equal to itself at the current number, and by the time the for loop finish, the sum will store everything. Well, okay, in this exercise, we actually compute the average, not just the sum. So after we have the sum, we have to divide by the number of elements in the list to get the average. Okay, so this is the algorithm that compute the average of a list of numbers. That it spans 4 lines. And let's say that if you, in the same Python script, you have another list of number, and then you happen to want to compute the average. So basically you repeat the exact same 4 lines, which is kind of annoying, right? Would it be nice to have a way to package these 4 lines into some sort of command or function, and then later on, if you want to execute those same 4 lines, you just like call the name of the command and give it the input, and it will do the exact same thing, but on different inputs, right? Think of like the point 3D command. Like the point 3D command, it do the same thing every time. It just construct a new point 3D, but it taking different inputs every time. That's why it gives different results. So the actions are the same, but the inputs are different. So the output varies, okay? But the type of action is the same. So that's what a command is. A command is just a way to package a piece of code so that we can use it multiple times. And this piece of code has custom parameters. So one way to think of it is a command or a functions, visually, it kind of corresponds to a component on just a normal grasshopper component. Let's say the component that create 3 points. Point construct. Okay, so this function is defined once, and it's defined and located in the ribbon, but I can like use it as many times as I want, right? And each time I give it, it's the same command, or the same grasshopper component, but if I give it different input, it's gonna give me different output. So in Python, the idea of writing a function is basically package it into a single command like this, and then you can use it as many times, and each time you give it different inputs, and then it will produce different outputs. Okay. So how do we define that functions? All right, so this is the syntax. So in the same Python code editor, we start with a brand new. So first we have to define what the function is. Now defining a function doesn't make the function runs yet. So as if you have a Grasshopper component defined in the ribbon, that component doesn't run yet. It just lives in the ribbon, right? You need to like activate it by taking it to the canvas and then give real input to it. Only then it actually runs, right? But the definition already there in the ribbon, okay? So here, this is the definition. This is not like the real usage yet, okay? We just define what will happen when we actually use it, all right? So this is a piece of code, okay? So to define a function, we have the keyword def, okay? So which stands for define, and then the name of the functions by convention. The function's name always use uppercase naming conventions, and also as a good guideline, because a function or a command, the function describes a command or an action, then in the name of the function you should give a verb, okay? So compute average rather than just say average, okay? All right, and then we open a bracket and have a list of input. Okay, we're gonna give it input a name. Okay, and here this function has only one input, and we name this input numbers. Okay, all right, followed by semicolon. All right, and then the body of the function is going to be written in such a way that all of the this mini program here, which make up the body of the function, has to be indented from the keywords definition. Okay, and remember this is a mini program, so it can be as complex as it wants. So this is a piece of a program or a piece of code that ready to be run. Okay, but not quite run yet. But okay, so this code runs and it do the same thing. So sum equal to 0, and then for each number in numbers. And what is number? Number is just the name of the input list, right? Okay. Of course, at this point, it doesn't know what numbers really is. So number here is just a placeholder, just a name waiting for a real list to be sent into that, right? And then sum equal to sum plus number. Okay, so this part is we already know, and then this function, it just run this thing, compute average, and display the value on the output panel. All right, so that's its definition of a function. All right, and then after we have the definition, we can run that function, and or we can say we invoke or we call the function. Okay, so normally the terminology when you actually use a function, you say we call the function. So calling the function is just a matter of writing out the function name. This time without the keywords def, because we're not defining it, we're activating it, or like we're invoking it. And we invoking it, so which means that we have to open the bracket and give it a parameter. So this is a function or just like a normal command, right? And whenever you use a command, you have to open the bracket and give it real data. Now this function expects only one input, and that input is a list of numbers. So we open bracket, give it one item, and that item is a list. Okay, and here I just declare, or I just like create a list right here and pass it directly. So 2, 3, 4, and 5. If I press the play button and run this whole code, it will print out the average of those numbers. Okay, which I'm gonna see some number here. All right, and here's this reusable part of the function. So here I invoke the function, okay, on this input. Now I can invoke the same functions, okay, but this time I give it a different input, okay, and then if I run, I should see two numbers, okay, 3.5, which is the average of the first list, and this is the second list. Okay, so anything, okay, we can copy and paste, but like if you run it, this is exactly what you get. So we're not going to try, because that is like a dry demo you see there. Okay, so some terminology. Okay, this is the function name. This is the name of the input parameter. Okay, but when you use the function, we say you call the function or you invoke the function. Okay, and when we invoke the function, we have to send in the real data for each of the input parameters. Now the real data, we call it the argument. Okay, so distinguish between the input parameter. Input parameter is just the abstract name, but the data that's sent into the input parameter, we call it the argument. Okay, so the list 2, 3, 4, 5 is the argument to the input parameter numbers. Okay, so when you look at the documentation and you see the word argument, you know what it means. Okay, so input parameters and argument are two different things. Argument is the data being sent to the input parameter when you actually used it. Okay, so this is just like, okay, this is like, again, this is a function, this is input parameter x, right? But the real value that you send into it, okay, this is the argument, okay, the argument that send into the input parameter or the input port x, okay. Right. Okay, so that's the first benefit of having a function. You write this piece of code once, and then whenever you invoke it, the exact same program runs, but it acts on different value of the numbers input. Okay, so it's gonna give you different result. Now the next thing is a function can also have an output. Okay, so this one, it taken 3 inputs, it do something internally, and then it send out an output, right? Now our functions that we define in Python does not require any output yet. Okay, so it just displays something on the screen, but this is not an output. This is just a display, right? It's not output in a program sense. Like if it's return an output, we should be able to take that value and store it in a variable. But here it just print out something. Like we cannot store that in a variable yet. Okay. So how do we modify this so that it return a value? And then it's up to us to take that value and output it on the panel ourselves. Okay. So the functions can do a own sort of logic, and then at the last minute, it will say return average. Return is the keyword, and then this is the value that will be returned to the main program. Okay, so it's compute the average and return the average. Okay, it will make sense in a moment. What does this actually do? So when I call these functions, compute average, forget about the result 1 equal. Okay, forget this part. Just look at, so this one we invoke the command or invoke the function, give it input parameters. It's gonna do something inside. Okay. And once it finishes, it will return average. Okay, so after this thing finished, I will get the value of average. Okay, so this whole thing, it runs for a while inside the computer. Well, just like very quickly, just a few nanoseconds, and then at the end of the day, you get one single number. Okay, and you're gonna store, and we're gonna take that number and store it in a Python variable result 1. So this time the function does not display anything on the output panel. It just returned a value to the main part of the program. Okay, to the main part of the Python script. All right, and then here's another example. I invoke compute average again. This time I get another number and I store it in a different Python variable. And now I have 2 numbers, and then it's up to me to do whatever I want with result 1 and result 2 further here. Okay, for this example, I will just simply display result 1 and 2 on the screen. Okay. All right. So how about if you look at a Python a grasshopper component, sometimes it has more than one output. Okay, the one I showed you in Python only send one output out. How do we achieve multiple outputs? I'm not sure if there's there is a deconstruct point that take in one input and return 3 outputs, right? So a Python functions can also return multiple outputs. Okay. Okay, so we're gonna touch on a new concept called a tuple. It's similar to list, but it's not meant to store a lot of data like list. It's just like meant to group like a smaller number of data into one single item. So let's say that for convenience, we want to define a function that computes the area and the volume of a cylinder. So this function takes in 2 numbers. The first number represents the radius of the cylinder. The second is the height of the cylinder. And then it will compute the area and the volume, okay? And then we have to return us 2 of the values, or the area values and the volume. Now the trick is that Python, a function can only return 1 item, okay? But if we want to return multiple items, then we have to somehow group it into one single item. and return that like bigger container item. Okay. Now, if you learned previously, we can group multiple items into a list, right? And a list is being treated as one single item. So we can like group everything into a list and return that list. But here we're going to do a slightly different. We're going to do a tuple. So a list meant to store a collection of data that is like going to be changed and new thing going to be added. But if you want to have a fixed structure, let's just say a pair of numbers that represent area and area volume, you can group them into a tuple, and the syntax is similar. So first, inside the program, inside the body function, we compute the area based on the input value of R and H. Okay, so that's just a standard high school math formula. And then the volume is similar. Okay, now we have to return both area and the volume, right? So this is how we do it. We package area and volume into a tuple. So the syntax to create a tuple item is the round bracket. If you use square bracket, it's going to create a list of two numbers. The first number is area and volume, but here we use tuple, okay? All right. Now, when we want, okay, so this is the definition of the function, and now we're going to use the function for real. We're going to invoke the function, give it two real numbers, 2.1 and 3.4. This thing run and return the result as a tuple. We're going to store that tuple into this variable here called result. And similar to a list, in order to retrieve the element from a tuple, you just give it, you use the square bracket operator and give it the index. So so this is a tuple of two numbers, right, or a pair. If a tuple consists of two elements, we call it a pair. If a tuple consists of like three elements, we call it like a triple. So result open bracket 0 will give us the first item inside the tuple, which is going to be the value of the area. Okay, so we retrieve it and we store it in a new Python variable called area and same volume. Okay, so the function pack the result in one tuple. We call the function, we get a tuple, and then we have to unpack it or like manually retrieve the right element. Okay. Now it's important to point out that the name area here and the name area here refer to two different Python variables. This is a Python variable lives inside the functions. Okay. This is another Python variable that live in the main part of this Python program. They happen to be the same name, but they're two completely different variable. Okay, and if you think, remember the mental image I told you, the variable is just a little part of memory. Okay, so here is just a different container or box inside the memory. It just happen to have the same name, but they are in different part of the code. So they are referred to two different things. Okay.
So, and could those be a list instead of a tuple, or?
This is a tuple. You can return a list, but doing a tuple is actually more efficient here. The difference is minimal in terms of performance. But when you want to return a fixed list, okay, a list that is not going to be changed or modified, use tuple instead. Tuple is meant for things that's not going to be changed.
The tuple only can contain two values.
As many as you want. Yeah, but once you create a tuple, you cannot append. Tuple doesn't support append or remove, or even like override an existing element. Okay.
Kind of simplified version of the list.
Yeah, it's a simplified and it has that slightly different. So usually lists contain many elements at the same time. So a list of points, a list of breadth. So they are different breadth, but they have the same type, which is the breadth, right? Tuple the first element can represent a name, which is a string. The second is an age, which is an integer. So that tuple describes the name and the age of one person. Okay, so it can contain data of different type, but those different entities relate to one entity, like so the same name and age of one person. And the list is about multiple entity. Okay, so the syntax is different, the program is different, but also the usage and the meaning that we use is different. Like so, one is to store multiple entity, while the white tuple is store multiple aspects of the same entity. So here we store different aspect, which is the area and the volume of the same entity, which is the cylinder. Okay, they happen to have the same data type, which is just number, but the aspect or the meaning are different.
When you call a different index, like a different data type, you have to, I can kind of understand what data type it is.
Yeah. So because we are the one who wrote this function, so we know that the first one is area and the second one is volume. But if this function comes from a library, which means that you don't have the source code, right? You have to look at the documentations in order to know what is being returned to you. Okay, and it will specify. Okay, we return a tuple where the first element is an area and a volume. Okay, Yeah, so a lot of functions in the Rhino common library doesn't give you the source code, or even if it gives you the source code, it doesn't necessarily mean that you will understand it anyway, because it can be very complex. So you look at the documentation and know what is the input and output. Okay, so here I retrieve the area and volume, and then it's up to me to decide what to do next with area and volume. But here I just stop here, or I just like print out a value of area and volume. Okay, so far all of this example just deal with numbers. So far we haven't drawn any geometry using function yet, but you're gonna see in a moment why function is useful. Okay, when we come to Rhino geometry as well. Okay, so those are conventions that I already mentioned. Okay, so I already mentioned the first 2 points. Now the third point is that the name of the parameter should use a mixed casing or camel casing. So it's just like a standard variable name where the first letter is lowercase, but whenever you have a new English word, you should use uppercase. Okay, now here is another benefit of using the function. So the first benefits we already know. So the first benefit is allow the code to be reusable, right? We write it once, we use it multiple times, okay? The second benefit is that it helps to abstract away many of the low-level implementation details of a certain actions. For example, the function compute cylinder volume that we wrote, there's two mathematics formula inside it. So the person who wrote it, or when we wrote the function, of course we need to know the formula in order to write a piece of Python code. But after that, whenever we use the functions, we don't really care what is going on inside the body of the functions. We don't even care about that mathematics formula. We just care that what is the name of the functions, what input is taken in, and what output it return, right? So when you write a complex function that has probably like 100 lines of code and you give it to your friend doesn't need to understand like that's 100 line inside. You only need to write a little documentation to your friend that say, okay, this function is gonna take in a breadth and then a number n, and then the output is like a skyscraper of n stories. Now the logic to output a skyscraper, it has 200 lines inside the body, but like your friend doesn't need to know that, okay? Unless he had a source code, he just know that, okay, give me a breadth, and whenever you give me a different breadth and with a number n, I'm gonna give you a skyscraper as an output, okay? So they abstract the details away, and a programming library like Rhino Common is basically just a collection of these predefined functions where, some of them are very simple, but some of them are very fanciful. For example, the function that computes the intersection between two curves. Okay, it's going to take in two curves and return an intersection point, which is point 3D, right? Now, the mathematics of finding the intersection of two curves is pretty fanciful. If you look at the source code, it might be very complex. But we, as a user of the function, we don't really need to care. We just say that, okay, give it two curves, and then it will give us a point out, okay? So that is why function is important to know. So even if you don't define the functions, we already use the functions that being defined for us all the time, except that I have been calling it commands rather than functions, but now we're going to stick with the real name of functions. Or as you see, this is another name called methods. So methods and functions and commands are kind of synonym. Okay. All right, so let's do useful functions with Rhino geometry. So the routine of compute midpoint. So actually, the compute midpoints is quite simple. In Rhino, just like say a plus b, and then divide by 2 or multiply by 0.5, right? But it's nice to package. Even though this program is very simple, it's still nice to package them into a function. And when we do if we package this in the function, we have the chance to give the function a name, right? So later in the code, if you say compute midpoint A and B, it's somehow more kind of meaningful to the person who read that code rather than seeing A plus B divided by 0.5, okay? So this is like a toy example, so we can, okay, so let's follow. So this is kind of a live example that has multiple steps. So I think I'm gonna base this one. We can carry on from Okay, we carry on from the next, from the previous example, okay? All right, so normally the way we, this is the same Python script, right? So normally we put on the definition of the function before the main part of the script. So this is the main part of the script where things actually run. So I'm gonna put in a command and say main script. And then do a separator line here. Okay. All right, so define compute midpoint. Okay, so this is just a definition of a simple function. We haven't used that function in the code yet, in the script yet. We just define the existence of it and what it's supposed to do, but it has never been activated yet. Okay. Okay, but just for testing, okay. So all of these programs, the script runs, okay, but I can ignore it. I go to the very last line, and then I will call the function. So this part is temporary. We can ignore it for now. Okay, if you want to, when you can remove it, but we're going to use it later. So if you want to comment out, so one way to temporarily deactivate own piece of code is, in case you can't ignore it. In this example, we can ignore everything here. But let's say that sometimes you cannot ignore it. Sometimes you really have to comment out. So we convert it to command by using triple quotations. So, okay, you can put a hashtag in every single line, but that's going to be pretty tedious, right? So another way to comment our block of code is to, at the beginning of this block of code, we're going to put in a triple quotation, and then at the end, we close it with another triple quotation, okay? So everything in here will be turned into command, so a quick way to deactivate the code. Okay, so right here I would say O geometry. So the output is going to be the result of the function compute midpoint. Okay, I give it 2 points now. I don't have input, so I'm gonna create the input point right here. Point, let's say free rg dot point 3d 567 for example. Okay, and I have one single point coming out. All right, so that's a simple function, and then we're going to use it to do a very simple case, which we could have done by hand, actually. All right, so now the next part I want to demonstrate is, once you have a function, you can use it anywhere. In fact, you can invoke it inside the body of another functions, okay? So, if we have a function and that function create a point 3D, then okay, we already did this thing that is, use the point 3D function. We invoke the point 3D function inside the definition of another functions. Okay, so, but now instead of using point 3D, we use another function that we define. Okay, so we already have the compute midpoint function somewhere in the code, right? Now we're gonna write another function. This time, this new function is gonna be create mid-line or middle lines. This function is gonna take in 4 points A, B, C, and D. And then we'll create the line that connect between between the midpoint of A and B and the midpoint of C and D. Again, this is like a silly, simple example. It's not necessarily why it's useful, but okay. And we can do the same logic with our function, but the point here we package all of the code inside the function so we can reuse it multiple times. All right, so we already have the function compute midpoint somewhere in the code. Now we're going to define another function called create a midpoint that take in A, B, C, and D, and this should return a single line object that connects between M and N, right? All right, so inside the function, first we have to compute M and N. So to compute M, we invoke another function that we used early on, okay? So this time, so we invoke another function inside the definition of another function, as you see. So compute midpoint A and B, and we should get M and then N, and then from that we can construct a new line. So line should be green. So let me fix the color a little bit. Okay. So lines command should be green. All right. So this is the definition of the function create midline. All right. Now we're gonna invoke the function create midline. Okay. And then create midline is gonna take in 4 points, right? Again, I have to fix the color to make it clearer to see. All right, so we're gonna invoke the function create midpoint, and we're gonna give it 4 points. Okay, if did you see the symbol here? So in Python, if you have a very long line and you want to break it into 2 different lines, you put in this symbol. This symbol will tell us that whichever come here is actually on the same lines. Okay, supposed to be on the same lines. So the backward slash symbol. All right, so okay, so create midlines. Give it 4 points. It's gonna output a line, okay, and then we're gonna send that line. So this entire big fat thing here. So this function is gonna give me 1 line object, and it's gonna send it to the output called O midline. So let's create another output called O midline. All right. Let's gonna do the function. Compute midline. Okay, so that's the definition. The midline should be here. Okay. I will remove the geometry. I don't need that. Right. Create the midlines. Why do I have? Okay, and I should get a single midline coming out right here. Okay. So just one comment I want to make. So you see, we define 2 functions, but in the main part of the script, we only invoke this function. Okay, but this function will we only invoke create midline, but we also indirectly invoke compute midpoint, right? So not every function you define has to be invoked in the main script. It's just there as a utility function to serve another functions, okay? Which is quite a normal thing to do. All right. Okay, so when we have a function that take in 4 points and return a midlines. Okay, so just a quick exercise. Let's compute this create midpoints to every group of 4 points. So here is just an arbitrary example 4 points, right? But let's apply this to the group of 4 points that we retrieve from the for loops. Okay, so let me delete this line because we don't need it anymore. Okay, then let's uncomment all of this guy. Okay. So in the previous example, we're gonna retrieve 4 points and we're gonna do some simple pattern on it. Now we're gonna do a pattern that that consists of 2 lines. The first line going from the midpoint to this midpoint, and then from this midpoint to this midpoint. and we're gonna write the code for compute midpoint, right? So we just need to invoke that code once, no, I mean twice for every group of 4 points. And we're gonna get 2 lines, and then we're gonna append those 2 lines to the list of lines here. Okay, so delete this guy. All right, so okay, so lines append. So now we're gonna need the to get the first mid lines. So compute mid line. Okay, now compute mid line gonna take in 4 input, right? Okay, my 4 input going to be, okay, the points as index I and j. Okay, the second input gonna be right here, gonna be index I plus 1 and j. Sorry, I plus 1 and j. Then the next guy, I plus 1, j plus 1. According to the logic, we say A, B, C, D, right? So A, B. So this one gonna be actually I, j plus 1 first, and then, okay. So the functions take in inputs as the order A, B, and C, D. So we say I, j, I plus 1, j, I, j plus 1, and then I plus 1, j plus 1. Yeah, I say create midline, you're right. With a good code editor, like if you type out a few words, it will show a list of autocomplete, and then you will rarely make this kind of spelling mistake, right? But this code editor is a bit horrible. The autocomplete almost like non-functioning. But in code editor, if you define a function, it will be like smart enough to. So if you type like CR, like an autocomplete will pop up, and then you will almost just need to press enter, and then it will complete the whole thing for you. For simple script, this one is fine, but like for a large program that is hard to debug, that has like more than 50 lines, I would use another code editor. For Python, it's easy to make another code editor works with this one, because you write a code in another code editor, and then there's an easy way to have that external script, which is managed by another code editor, to be invoked using this main script. For Python, it's relatively easy to do so. Okay, now if we output lines, then we have, a bunch of lines connecting. Okay, I want to output the point as well. So O geometry, we output lines, and you know what? Let's output lines into O mid line. Okay. This one should be plural, but I name it singular, so let's fix that. And then O points, O geometry should be just the fast list of points, just so that I can like compare them on the screen together, points and lines. Flattened. Okay. Okay, and now if we want to do the other directions, then we just need to shuffle the index a little bit. So let's do another line, but like it's gonna be a mid line, but in another directions. This time we just need to, okay, it's gonna pretty mess up my head a little bit now. Okay, I think we're gonna swap the first and the second, and the third and the fourth index. And then we're gonna have the other dimensions. No, actually, it doesn't work like that. No. So second and third, and swap the first with the fourth. Let's try that. Still nothing. Basically, it just got the exact same line. Okay, but basically, you just got the right index. But anyway. Second and third one. So just swap the second and the third index. Okay, good. All right. Yeah, so we invoked the function inside the for loop. All right. Now, just want to comment. Now, if you experience, you will realize that this function is overly complex. Like, if I want to do a function that compute a midline, this is how I would. I wouldn't need to define a function separately. So this is how I would do it. I would say a plus b. You don't have to do this, okay? And then c plus d. I don't need these two lines, okay? And I don't even need to compute midpoint, all right? Now, of course, for demonstration, I kind of split it into like slower, smaller steps and package them to smaller functions to demonstrate the fact that you can call another function in another function, okay? But in this case, it's too simple to even like structure in like two separate functions, all right? But in real case, you're gonna see that it's helpful to if you have a routine that like do so many things in common, it's helpful to package into a function. So for example, the if you have 1 point and you want to compute if you have a group of point cloud and then you want to have another point, a reference point, you want to compute the shortest point among those point cloud to your reference point. Those are kind of a common routines. So you can package that those code into a function that take in a list of points that represent a point cloud and another single point that represent the reference point, and then return the single point from the point cloud that is closest to your reference point, for example. Okay, let's. Okay, so 3 types of function that you will commonly see. So only the function that we wrote so far are just called normal function or standalone functions, where it doesn't have any data of its own. Like, so you have to give it extra data for it to function correctly. Now I can write a function that doesn't need any input parameters, but that case where you write a function that doesn't have any input parameters. For example, this is a very stupid function. First definitions, let's say print I love you, for example. And this function doesn't have any input. It just, whenever you run it, it just prints out a message I love you for 50 times. So it's very silly functions, but it's a perfectly fine example. It doesn't have any output, it doesn't have any input, but it does do something in the computer, right? So print I love you. All right. So next time, if your teacher asks you to write something on the board as a punishment, let's say I will never do it again, you should say for I in range and then print I will never do it again. Okay, for example. All right, so that's a perfectly good example. Okay, another useful example. Okay, if you want, okay, let me give you a useful example of a function that doesn't have any input. For example, you can write a function that automatically generates, let's say, 100 box of different size without any input, because it's a fixed program, and then it doesn't have any output in the sense that it will, okay, do 100 box. Then programmatically bake the box into the rhinoscene, and then for each of the box, it save each of the box into a different 3D M file. Okay, so it's perfectly useful program that function that doesn't have any input and doesn't have any output, but it still do something useful. Okay. Okay. So anyway, so the function that we written is a standalone function. So whenever you invoke it, you just say the function name without any prefix. Okay. So this is the first time I should have showed the missing comment here. So type 2 is a functions. Another type of function is a functions or a command. We've been calling it command, but now we call it a function. The second type of function is a function that is associated with a specific data type. Okay. For example, the functions or the method dot distant to is defined to work with any object or variable of type upon 3D. So in order to use these functions, you must have a variable that store upon 3D exist somewhere in your code first, right? And then you can activate or invoke these functions after you have this the variable. So you have the variable name, and then you say dot, and then the function's name, okay? And then the input parameters. Okay, so this function requires an existence of a variable to be invoked on. Now, this kind of function, so when a function is associated with a specific kind of data, in this case pon3d, we call it a method. Basically, it's just a function, but it's different from a normal function. It's different from this type of function. So in programming, people give it a dedicated word or name to call it. So it's called a method. All right. But it's still an action after all that takes in an input parameters, except that it will also use the data from this variable. So in order to compute a distance to, you need to know some data of the current point, right? Not just the target point. So this function has access to all of the inside. If you look at the definition of the function distance to, well, we don't have access to the source code. But if you look at the source code, of course, it needs to query the XYZ coordinates of this host point in order to do the math. Okay, so that's type 2. Now another type of functions is a static functions or static method. Now this function is also associated to a data type, but in order to use it, you don't need to have a variable of that data type first. You just need to invoke it on the name of the data type. For example, the data type vector 3D or the class vector 3D. If you look at the documentation, it has a static function called cross, which computes the mathematical cross product between two vectors. So this function is going to take in two vectors object, okay, and return the result, which is another vector. But anyway, the way you use it is that you have to prefix, because this function is a static function defined within the data type vector 3D. Then when you want to use it, you have to say the data type name first and say dot and then cross, okay, and then just input parameter. So these two are kind of seem to be similar, but they are different in the sense that this one is invoked on a variable of the type pon3d. This one is not a variable. This is just like a data type name, okay, which is vector 3D, okay. Now the reason why it is defined as a vector 3D is just because when you have a lot of functions, it makes sense to group them into certain data types, right? And so when you look at the libraries, they organize the functions into data types, okay? Here, this is the function that we define by our own, so it doesn't need to be prefixed by anything when we use it, okay? But like if you have like 1,000 of functions, it makes sense to group the functions into an associated data type, because this cross function here is related to the vector 3D, so that's why it is defined inside the vector 3D data type, okay? All right, so if you look at the Rhino Common documentations, now I hope everything will make more sense when you look at the Rhino Common documentations. Everything is inside the Rhino Common library, and hence the documentation is just a large collection of predefined functions. But these functions were defined within certain data types or associated to each data type. So let's look at the function is perpendicular to. So this is the name of the function. This function is defined for the data type vector 3D. So that's why when you use it, you have to say vector 3D In fact, you have to say rg dot vector 3d because vector 3d lives inside the library rg, right? So you say rg dot vector 3d, and then doc is perpendicular to, and then open the bracket and give it 2 input parameters or 2 arguments. The first argument must have the data type vector 3d, and the second type. Why we need a double? Oh, double is just a tolerance. Okay. No, this is not a static function. So this function is a normal is a normal method, which means that you must have a variable of type vector 3d. Okay, so okay, let me write it out in a sample. So if you have 2 vector 3d that start in first vector, okay, and okay, I give it a value vector 3d 1 0 0 0 0 0. And a second vector has slightly different value. Okay, so first vector is a variable of type vector 3d, which means that if I say dot, okay, and because there's no autocomplete here, but if you do, in a good code editor with autocomplete, then it will list out all of the functions that you can invoke on a variable of type vector 3d, and in that list of like available function, you should have the dot is perpendicular to, okay, and is perpendicular to will take in another vector and a small number for tolerance. So if I say is perpendicular to, give it another vector and a small number as tolerance, okay. This thing will run and it will return a value, and that value has data type boolean because it's perpendicular to, it runs and it will return yes or no, right? So the data type, the answer is has a data type boolean, so it's obvious. Okay, if you look at documentation, it's a return value. So if you look at this one, it just tell you that the data type of the return value is boolean, but the meaning of that is something that you have to look down here. Okay, in this simple example, of course, the meaning of the return is the answer to the question: is the first vector is perpendicular to the second vector? But in some more non-obvious case, you have to look down here to see the actual meaning of the output. Okay, true if vectors is 90 degrees, otherwise not. Right? So the return data type, the name. So this is the syntax of C#. In C#, the function was defined using slightly different syntax. So the function name, the input name, but in C#, in the C# language, for each of the input parameter, you also have to specify the data type of the input. In Python, we just like say the input name, okay, but not the data type. And also in Python, the function definition also specify the type of the return data, but in Python we don't even specify that. Now the documentation is written in C#, okay, but when we can use it from Python. So when we use in Python, we just say we have a vector and then we say dot is perpendicular to, give it two variables, two input arguments to the input parameters. The first has to be vector 3D because the documentation clearly expects it to be a vector 3D, and then a double. All right, if I run this, well, this whole thing, remember, will be a Boolean value. If I print out as Boolean value, I should get either a true or false message. So let's say false because this thing is not perpendicular. Okay, just to demonstrate. So this functions, the person who wrote it expect this thing to be a vector 3D and this thing to be a number or a double, right? And the documentation clearly says so. If I give it like 2 number, of course it will complain. It will say that expecting a vector 3D, but got a float or like a number. Okay, so I think I mentioned this part in the first lecture where when you call the functions and then you throw data into it, the data type of the input parameter or the argument does matter. Okay, so function expect to receive the right data type. Okay, so why don't we take okay, I don't think we need a break. We're gonna have only like half an hour left, so let's press on. All right, so now with function, which is a pretty dense topic. So randomness. Let's switch to a more fun topic, randomness. This one is separate from functions, but you can use it from within the functions, obviously. Okay, so how to generate random integers and random numbers in Python, and then we're gonna use those numbers to generate geometry as well, right? So this part is not live. This part is just like a dry example, and then we're gonna do a live example when it comes to geometry. So first we have to import the random library. So we have the math library that support the math.cos and math.sign and all the mathematics commands or functions. Now all of the functions that generate random numbers live inside the random library. So import random. All right, and then if we say random, the library names, okay, and then dot, then we have access to this function. So rand int. This function will take in two integers that specify the minimum range and the maximum range. And this function, whenever you run it, it will give you a different random number between 0 and 4. So it's always exclude the last number. So it's 0, 1, 2, 3, or 4. Okay, and we store that random number into my random numbers, and then we print it out. Okay. If you okay, okay. So I think that's fairly self-explanatory. Let's go to the next example. We're gonna try out the last one in a second. If you want to do 10 random integer, of course you just need to run the same code inside of for loops, right? Or just like copy and paste that code 10 times. Okay. Now this time we run, you will see 10 random number being printed out. Okay. If we want to do decimal number between the range, let's say 1.2 and 5.0, then we it's gonna be similar, but this time we're gonna say uniform. So it's gonna give us a random number that is uniformly chosen. That is chosen with like uniform or equal probability in the range between 1.2 and 5.0. Okay, so let's copy and paste the last one into a brand new Python component. Okay, and we should see 10 random numbers being printed out. And if you look at these 10 numbers and compare to the 10 numbers on your friend's screen, you're gonna see that they are different. They are truly random. Okay, so it's not really a trick here. Okay, in fact, if you press the play button again, and you get every time you run the script, you get 10 different random numbers between 1.2 and 5.0. Okay, so many of you, so next concept, many of you already know that is about the seed of a random number. So what is a seed of a random number? So when I kind of semi-lying to you that these numbers are random. So in computers, there's no such thing as random. Like when you in computer, everything is controlled by the electric circuit, right? They run so deterministically. Actually, forcing the electric circuit to run in a random manner is actually really hard. So to generate random numbers in computers is kind of not possible in a literal sense. So all the random number you see here is kind of a trick. So what happened is that when you say uniform, it actually has a predetermined number inside the memory. And then there's a fanciful algorithm that takes this number and apply a weird mathematical process to it to transform it to a seemingly random looking number. Okay, and then if you call random number uniform again, it would take the last random number and apply a weird mathematical rule and bring it to another number that looks seemingly random and totally unrelated to the previous one. But the rule of transforming all these numbers are fully deterministic, which means that if you run the whole procedure again from the same original number, you guarantee to get the same sequence of so-called random number, but they are fully predetermined. Okay, that is why we call them. So here we call them random number, but actually the real terminology is we call it pseudo random numbers. So they fake random numbers. So they are not random. They look chaotic. So there is difference between the word random and the word chaotic. So all of the sequence number here look chaotic, but they are not truly random in a literal sense, right? So here, before we run, let's say random, and then we can choose a seed number, which is, let's say, seed, and the seed take in an integer, okay? So we set the seed of the random generator to 0, and this time if we run it, if we run the random.uniform, we're gonna get the same sequence of numbers. So if you run 0 and your friend runs seed 0, you will get the same sequence of number. And no matter how many times I press the play button, I will get the fixed number, the fixed sequence of numbers. Okay, that looks chaotic and seemingly random, but they're not that random. Okay, if I change the seed to another number, then I will get a different sequence of chaotic or pseudo-random numbers, okay? If you don't specify the seed, then what happens is that Python, the random library in Python will automatically choose a seed based on usually the time on your Windows operating system. So it trick you to, so it gives you a different seed each time, and it even trick you to thinking that everything is random. But okay, again, it's fully deterministic. All right. So random seed is useful because when you want to generate something, if you want to write a script that generates random geometry, and you want to debug it, normally you want to keep the seed fixed. So each time you run it, you get like the same outcome, so you can compare to the previous outcomes and know if there's something going on. After your script running perfectly fine, you can remove the seed and then let everything run truly random. Okay, but for debugging, it's kind of helpful to have the seed values. All right. So let's apply this to generate random geometry. Okay, so a Python component that has iCount, which is the in. Okay, so let's prepare this very quickly. Okay, Python. The first input is the number of random pointers that we want to generate. So iCount, which is an integer. And then the output is again geometry. All right, the script. I'm gonna copy and paste because we're slightly short on time, and the script is very simple anyway. All right. So we have an initially empty list of points, okay, and then we're gonna have a for loop to repeat this random point generations over multiple of time. Okay, don't forget to input in some number for iCount. I would say 200. Okay, so we just generate a random coordinate, a random number between 0 and 10 for the x coordinate, and then another random number for y coordinate, and then we use that to construct a new point. So as simple as that. And again, if we don't set the seed, and every time we run this, we should get a different sequence of random number, and a different sequence of points. Okay, as a quick exercise, let's create a list of spheres. Okay, and now here for every point that you generate, I want you to generate a sphere that has the center as a point, but with random radius. Okay, that's just a quick exercise. And don't forget to change the output to spheres rather than points, otherwise you won't see anything. All right. All right. Now the next part is important. So the takeaway message is randomness does not have to be completely chaotic. By applying some simple mathematical tricks, we can control or vary the amount of randomness or blend randomness with perfectly orderliness, or if there is such a word in English. All right. So give you a simple example with this one. So here, rather than using a simple a random radius, what if we correlate or relate the radius to the xy coordinate, which means that the larger the xy coordinate, the larger the radius. So the radius can be x. So x and y itself, x and y themselves are random. But let me replace formula here. So the radius is gonna be x plus y. Okay. So x and y can be random, but the larger they are, the larger the radius will be. Okay. So, but anyway, that would be too large. So I will scale it down to maybe 0.1 times x plus y. All right. So what you see is that the radius at this corner here, we're going to be larger than this corner. Okay, so if I run this, okay, this still be a bit overwhelming, so I'm going to reduce the scale factor a little bit smaller. But yeah, I hope you see the effect. So the x and y are random, but the radius are based on those random value, and it had a certain correlations, right? Okay. And what I did is just I changed a very short part of this line of code. All right. So okay, so all of the example that we have done over the past 2 weeks and also this week, all of them, literally all of them, can be replicated using just Grasshopper Visual Components only. And this will be true until until December. So the first time we're gonna ever learn an algorithm that is not possible or very hard to achieve using Grasshopper Visual Programming alone will be in December. So for now, we just learn Python programming language. We learn how to use a random carbon to generate simple geometry, and then we apply rule to generate, but all of those rules are deterministic rule or straightforward parametric rule that can be done with Grasshopper. Okay, so you won't see the so at this stage you don't quite see yet the benefits of learning Python, because everything you've done here can be done in Grasshopper. Okay, but later on, after we familiar with all the Python syntax, when we come to the computation design and generative design algorithms part, then you're gonna start to see the power of textual programming language as opposed to visual programming language. There's certain logic that visual programming language cannot capture. All right, so let's go to the next example. We already know how to generate points on the 2D grids, right? And start it in a nested list. Here we just use a linear list. This example we don't need the 2D nested list structure, so we don't need we can start everything in 2D list. Okay, let me copy and paste this. Let's create a new Python component. The input going to be a decimal number, so a float. Okay, the name is going to be I variations. So variation going to represent how much randomness we want to put into the XYZ coordinate. And the point is going to be O geometry. Okay, and for the I variation input, I'm going to have a decimal number between. Okay, just put in some arbitrary number for now. All right, good. Okay, so this part of the code should be very obvious by now. It's just a grid point, 60 column and 30 rows. It's just a regular grid point. There's no randomness yet, so copy and paste it in. That's slide 28, by the way. Okay, and now here's the important part. So previously we generate a uniform random number between 0 and 10. Okay, so everything's like completely random. But here we take a slightly different approach. We start from a completely orderly grid. Okay, so x equal to I, y equal to j, no randomness there. Okay, and now here we add the random modification. So from the fixed coordinate I and j, or from the ordered the orderly position I and j, we're gonna add a small random uniform. Okay, so we're gonna give it an offset, a random offset between minus 0.1 and 0.1, and same with j. Okay, so if we add in those two random variations, okay, then everything will start to look a bit random, but it's still, you see the influence of the original grid are still there. So it's not completely widely random like in the previous example. Okay. All right. Now, as you might notice, the larger we allow the range of uniform to be, the more disorderly they will look. So if I increase this to 0.3, the range, if I increase to 0.3, things will look more random. You know, it will lose the grid position more. In fact, let's make this number here rather than a fixed number. Let's make it an input parameter. So we already have I variation here, right? So we replace this 0.3 or whatever with I variations. I variations, I variations, and I variations. All right, and now if you change the I variation slider, you will see that the amount of randomness will be changed accordingly. Okay. Okay, here's the effect of the seed. So here I don't set a seed. So every time Python will like do a completely different sequence of random numbers. So that's why every point like look kind of jittering all over the place. But if I put in a fixed seed, you will see that you will get the same sequence of number, only the scale or the offset scale is changing. Okay, the same sequence of random number, so not jumping around anymore. It's just the scale of the randomness range is changing. Okay, so that basically give you the kind of another hint of that, yeah, you can control the randomness. So in fact, if you do a random point within like a region, like in the previous example, this one, no, not this slide. So this is the first, damn it. So the first example that we did, in this way, we has almost no control over the randomness, apart from like the range, like the overall bounding box. And if you generate random numbers in this way, or random point in this way, even though the random numbers are supposed to be uniform, if you look at the distribution of the points, they are not that uniform. They are kind of, there's some annoying clump, or lump of a cluster of points, right? But if you use the technique where you start from a regular grid and then you add a slightly offset, then things are random but somehow like more uniformly distributed. Like you don't have any like large cluster of like annoying large cluster of points that like annoying, that like visually annoying. Okay. And later on, for many example, like for many, okay, let me think of a use case where you want to like have a fairly controllable or even distribution of points. Let's say that you want to set up, generate. Let's say if you want to do robot programming and you want to generate a little environment for the robot to navigate around, right? And you want it to be random rather than just a grid point, then this is probably a good case where you generate a bunch of obstacle object and see how your robot navigates. Or later on, we can use it as an environment, and then we're gonna have some flocking simulation that running through this kind of geometry, and then we can record a part of the flocking, and we'll create an interesting pattern. Okay, so the next example is, let me change the formula slightly. Instead of using I variation inside here, I just like put this into minus 1.0 and 1.0, and I put the I variation in front. So I variations times a random number between the range minus 1 and 1. So this is basically give you the same effect as before, but I'm going to show you why I write it in this form. It's just make it easier to do the next step. Okay. So normally with random number, people often generate a so-called unit random number. So a random number that run between 0 and 1.0 or minus 1.0 and 1.0. And then after you got that unit random number, we scale it by multiplied by the scale factor here. Okay, so I variations, I'm gonna keep I variation fixed, okay, which is 0.5 for now. Okay, so now I variation is basically a number that I input in. So every row and every columns has the same value for I variations, right? So the amount that they are allowed to offset is pretty much the same. Now, here's a question. Rather than using a fixed number of I variation, what if we compute the variation that depends on I? So hang on a second, you don't have to do this step yet. So I variations, okay. So if I do something like this, okay, nothing changed yet. I just like store I variation in not a variable called variation, a local variable. Okay, so this is a fixed value that come from the Grasshopper canvas, right? But instead of using a fixed value for all of the column I, what if I make the variation depends on I? So as I change, because I go from 0 to like 59, right? I want the variation to change, right? And remember, the larger the variation, the more the range of the uniform will be, right? So I use this simple formula. So I variation equal to 0.5 times I divided by 59. So let me explain. And then, so I will run from 0 to 59. So I divided by 59 gonna be a number that run from 0 to 1, right? And if I scale it down by 0.5, then overall this thing will run from 0 to 0.5. So the first column will have 0 variations. Everything is completely ordered. And then if I slowly move to the next column, I will increase. And then the value of variation will increase slowly. And if I use that variation to do the random points, then okay, so first column, the variations is nothing, but then the variation gonna increase. And then, yeah, you see? So another way to control the amount of randomness, okay? Okay, so let's try that. All right, the final bit is how to generate colors, okay? So this is gonna be probably useful for your assignment today as well. Okay, this is just an explanation. So in Python, we can generate a programming object or a programming variable that represent the color. But when you output that color, you won't see the color on the screen. So like you have a color in your script, but you know the color will not be displayed correctly. So we have to output that color and plug the color together with the geometry into the preview components. This is one of the built-in components inside Grasshopper. So we need this extra component in order to display the geometry in our desired color. Okay, so to create a single color, we use the command from RGB, from ARGB, which is a command or a function from the data type color, which lives inside the library system.drawing. Okay, so import system.drawing, and we give this library a nickname, drawing, and then we say drawing.color, and then dot from ARGB. ARGB, we're gonna use the version of this command that's taken 3 integer. The first is the red and green and blue channel. The number has to be between 0 and 255. Okay, so this one will create a blue color, and if we output the blue color and we plug the blue color into the preview, then we're gonna see the sphere being displayed as blue. Okay, but we can output a list of colors. So for example, if we give this preview component a list of objects, a list of geometry object, and then a list of color, then each of the object will be colored using the matching color from the list. So, all right, so now rather than creating one single or manually creating one single color object, we're gonna create a list of colors objects, okay, or color variables. And then each of them have a slightly different value, and the value are controlled by the by the logic of the for loop. Okay. So this is where our code is. All right. So now let's make another output. First, we have to make another output called oColors. So oColors. Okay, and now the code. All right, so first import the system.drawing library, and then we have an empty list of colors. Okay, all right, and in the for loop, so every time we have a list of points, after we create a point and append to this point, we also need to create a color for this particular point and also append to the list of colors. Okay, so let me compute the integer that represents the red amount. So here, this is again another simple formula that depends on I. So as I go from 0 to 59, this value here will increase slowly from 0 to 255. Okay, so the red amount will, so the first column will have like almost no red, and the last column will have full red saturation. The blue is going to be, I don't have to say, I would say, I can just simply say blue equal to 255 minus red. Okay. So the more red you have, the less blue you have. Okay, so basically it's just the opposite of red. Okay, and then finally for green, I will just keep it at 0. Okay, so here I can construct the color variable. Okay, from RGB, red, which is came here, green I keep it 0, and then blue, and then I append color to colors, and then I output colors. Okay. Okay, and colors.
Why is there a semicolon?
Because it's my habit from C#. But if you put it there, it's still fine, because Python allows you to have multiple commands on the same line using the semicolon. If you don't have anything afterward, it's still fine, right? So it still run actually, but it's redundant. But in C#, every statement has to be terminated by the semicolon, so it's like a habit that I always have. Okay. Alright, so colors. Okay, import system drawing. System.drawing is actually a standard C# library. This is not Python actually. This is one library that's come with the C# library that almost come with default with your Windows operating system. So if you install Windows, you already have this library, almost. Okay, and then we output all colors. Okay. Now we don't see any. Okay, so if you hover the mouse, you see 1800 colors coming out. So that's look correct. We just need to run this to put this into the preview component to actually see the color display. So geometry go in here, and color go in here. Okay, and you see how the color shift. Okay. All right. What if you want to do? So here the colors is not random, right? It just be controlled by I. But of course you can put a random formula to make the color random. So just for example, it's gonna be 255 times a random uniform. Or actually, I just generate a random integer. So random dot randint between 0 and 256. Okay, because actually we stop at 255, so I'll go one extra. Oh, it's actually inclusive. So let's stop at 255. 0 from 255, and then you see a bunch of random color. Okay. Okay, so this part is not on the slide, so you just need to remember to watch the last bit of the notation of the recording. Okay, another way to control random is here you have a random variation between red and blue, right? But it's not. It's like a spectrum of red and blue, not just like two choice, full red and full blue. What if we want to color them either using full red or full blue? So we're talking about different kind of random here. The random that we're doing here is called continuous random. So the value is like a continuously random value being uniform distributed on an axis line, right? So a number axis between -1 and 1. That's all the kind of random. It's called discrete random. That is the kind of random that describe like how a dice or like a flipping coin, because the outcome is like 6 discrete cases in the case of a dice. Or when you flip a coin, the outcome is not a continuous number. It can be either up or down, right? So how do you describe that random discrete event? So let's say I want to color each of these points either red or blue, or imagine, let's say you want to do a facade, and each of these are a curtain panel, and you want to say, I want to randomly put in either a solid wood for the panel or transparent glass, okay? But I choose them one randomly, okay? So those cannot be described by a continuous number, but it's described by a con flipping kind of logic. Now, how do you achieve that? Okay, so here, so let's say if, you know, I'm gonna give you the code in a second. So if, you know, I flip a con, and if the con is up, so like if con is head, like hit with the head, then I'm gonna append the full red color to the list, okay? Okay, this part we haven't explained how to do it in Python yet. Okay, so I'm gonna give it so drawing dot color, and then to create a full red, you're gonna give 25500. But there's also pre-existing defined values. I would say color dot blue. So this is one of pre-existing value. Okay, now else I will append the fully saturated red color. Okay, so this logic is a random if and else, right? So it's not like a continuous formula anymore, but it has an if and else in it. Now, so how do we generate an expression that is, let's say, true half of the time? So if you run this thing for 10 times, okay, actually we run it here for 1800 times, right? But on average, half of the time this thing will be true, and then you will have half of the time you have blue color, and the other half you will get red. Okay, so how do you achieve that effect? Now, so in statistic, which is a branch of mathematics, you know, there's a technique called Russian roulette. I'm sure you know what is a roulette, right? The spinning game, but do you know what Russian roulette is? Okay, good. So this thing is actually called Russian roulette. I don't know why, but okay, this is Russian roulette. Every year I Google Russian roulette when I teach this lecture, and the image keeps changing from year to year. Okay, so Russian roulette is a discrete random event, right? Okay, so how do you simulate that? But this random event is like more sophisticated than the point, because the chance is not 50-50. It's the probability of being killed, or like getting the outcome, is a custom number. In this case, it's a 1.6. So not only that we want to generate random discrete, we want to control that probability, right? So not 50-50, but let's say 1/5. So let's say 1/5 of the time I want to have a glass panel, but the remaining 4/5 of the time, or 80% of the time, I want to have like solid random. So how you do it? So it's actually fairly simple. You just generate a random uniform number between the unit range, so the range 0.0 and 1.0. Okay, and then ask if this thing is less than 0.5. Okay, so half of the time this thing will be true, right? And the other half it will be false. Okay, so you imagine you have an axis number, and then you pick a random point, and if it falls into the left compartment of that axis, then you perform the first event. If it falls to the second compartment, so it's like Russian roulette, because you have like 6 different. Here you have 2 different compartments. Okay. So if you run this, random uniform 0.5. I'm missing something here.
I think you have color instead of color.
Yeah, this should be red. Okay, so this time it's just pool red and pool green. But if you count them, on average, they approximately like half of them are red and half of them are blue. Okay. Now here's the interesting thing. You can change this like threshold. So let's say that I only want 20% of the time it's blue. I gotta make it 0.2, right? So only about 1/5 of the points are blue this time. So you see, you can play Russian roulette with a custom probability here. Okay. What if you have 3 possible outcomes? Then you just need to divide the axis from 0.1 into 3 different compartments, right? And then you have 3 if statements. Okay, you have an if statement. You have to split them into 3 different compartments and see which compartment that random number falls into. So, for example, if this thing is fallen between 0.2, I do blue. else if, or for shorthand is elif, which is short for else if. If this thing is no, actually I have to do the random number first, otherwise I will keep getting a new random number every time. So I would say random number equal to this random number. So I have to generate and fix it here. And if this random number is less than 0.2, I'm gonna do blue. If it is greater than 0.2 but less than 0.6, I will do red. Else I'm gonna do green. Okay, so 3 possible outcome. All right. So let me give you a final touch. Okay, so let me reverse it to the previous logic, which is blue and red. Okay, and everything, remember the probability between choosing either blue or red is controlled by this number here, and this number is 0.2, which is the same for every single column, right? Each column, when they play this Russian roulette, it uses the same probability. What if you want this probability to change? So the first column, the probability of picking blue is very small, but like slowly the probability of like picking blue is very large. Now why this is useful? Like imagine that you in the previous example, we can have a gradient shift between blue to red with a full spectrum, right? But let's say if you want to build this thing out of material, then you can either choose between, let's say, wood or glass. You cannot blend a panel between half wood and half red. You can have only 2 outcomes. But you want to do these 2 outcomes in such a way that overall, when you look at the entire facade, you still see the gradient between this thing is like has a lot of wood, but slowly it will translate to glass panels only. So you can have a gradient, but like with only two type of building blocks. Okay, so what we do here, it is threshold. So the threshold should be I divided by 59. So the threshold is very small at first. So first I equal to be 0, right? So at first the threshold is 0, which means that there's no way you can have a blue. Everything will be red. But slowly the chance of being blue will become more and more, and then by the time you reach the last one, everything will be blue. Okay, if I run this, you see, still 2 discrete color, red and blue, but you see the gradient effect. Okay, right. Okay, so this part again is not in the slide, but it's in the recording. So, and I will also save this file for you. So, all right. So now we can go to the assignment. Random colors with Russian roulette. Okay, so your assignment. Okay, it has this one. Now you learn kind of enough tools to have a kind of open-end creative design exercise. So task number 2 first. So task number 2, what you have learned to generate like some interesting design pattern. It doesn't have to be architecturally related, but if you can make it into an architecturally related, a little shell or whatever, then you can go that way. But you don't have to restrict yourself in that if you don't want to. Okay, the logic has to use at least one for loop. Like I don't want you to use a Python script to just recreate something that you could do easily by clicking mouse or a keyboard. Right? There must be a for loop to generate a bunch of like rules or logic. All right. So that's task number 2. So this is kind of an open-end task. Now task number 1 is just to practice writing functions. So writing a function that's taking a list of points. Okay, a list of points in order and return a list of lines. Okay, so we haven't done any example we haven't done any example of the function that return a list. So all of the function that we did so far return either a single item or a tuple. This one it return a list of lines that connect these points in the same order. Okay. Now of course after you define the function, you have to invoke it and give it the real data, which is like these points here to test the outcome. Okay, so these are the points. All right, this one is optional because I think you're gonna spend most of the time here. So this one is from the one who find this so easy, and if you want to challenge yourself a little bit more. So this one has slightly some algorithm in it. So it will take in a bunch of points again, and it will try to compare every possible distance between every possible pair of points. Okay, so you must have a kind of logic that cross-check every single pair of points. Okay, the first one is not about every pair of points. It's just like pair of points that follow in a sequence. But this one, you have to cross-check every pair of points and return or decide which pair of points has the largest distance among them. Okay, so this is kind of common problem. You're giving a bunch of point cloud and you want to pick out the furthest 2 points, and then this furthest 2 points can give you a good approximation of the size of the point clouds, right? If you scan an object, which give you a bunch of point cloud, and just like by picking the first largest 2 points, you can have a good, and using the distance of these 2 points, you can get a kind of approximation of the size of the points. Okay, all right. So this one I should put in another hint. This is again optional. You do not need to create any extra list in the script. So the only list that you have is this one, but the logic itself doesn't require you to create any extra list, even though you can, but it's unnecessary. All right, so this is more like a hint rather than a requirement. Okay, so that's it for today. Let me save the. All right, great. See you next week then for the final lecture before the introduction to robotic week start. All right, I'm gonna stop the recording now.